Hello and welcome back. In today's video, we're overclocking the Ryzen 9 9900X all the way up to 5825 megahertz. I do that using some of the AMD Precision Boost Overdrive tools like Fmax Boost Override, Curve Optimizer, and Scalar. I'll also be using the Asus ROG Crosshair X870 Hero motherboard and AIO cooling. In this video, I break down the Ryzen 9 9900X tuning process into 4 unique overclocking strategies for beginners and advanced overclockers. However, before we jump into the overclocking, let's first have a look at the performance at default settings. The AMD Ryzen 9 9900X is part of AMD's Zen 5 based Ryzen 9000 desktop processor product line codenamed Granite Ridge. The 12-core Ryzen 9 9900X is the successor to the Ryzen 9 7900X, which we overclocked in SkatterBencher number 46. It has a base clock of 4.4 GHz and a listed boost frequency of up to 5.6 GHz. Its TDP is 120 watts. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications and games to measure performance and ensure system stability. I use the following tools to check and log system telemetry, adjust clock frequencies, and launch benchmarks. Before we start overclocking, of course, we first have to look at the performance at default settings. The default Precision Boost 2 parameters for the Ryzen 9 9900X are as follows. The Ryzen 9 9900X has 2 CCDs, each following their own factory-fused voltage frequency curve. Here's the benchmark performance at stock. Here's the game performance at stock. Here are the 3DMark CPU profile and OCCT benchmark scores at stock. And here's the AIDA64 memory benchmark scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4242 MHz and CCD1 effective clock is 4236 MHz with 0.974 volts. The average CPU temperature is 68.4 degrees Celsius. The average CPU package power is 139.3 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 4823 MHz and CCD1 effective clock is 4778 MHz with 1.061 volts. The average CPU temperature is 71.4 degrees Celsius. The average CPU package power is 148.8 watts. We can of course increase the maximum power limit by using Precision Boost Overdrive, and that's exactly what we'll do in our very first overclocking strategy. However, before you start changing any settings, make sure to locate the CMOS Clear button. Pressing the Clear CMOS button will reset all your BIOS settings to default. In our first overclocking strategy, we simply take advantage of enabling AMD Precision Boost Overdrive and AMD EXPO. With the launch of Zen 5, AMD launched an improved version of their Precision Boost Overdrive 2 overclockers toolkit. Using this toolkit, we can adjust some of the parameters governing the Precision Boost automatic frequency boosting technology. The Precision Boost Overdrive 2 toolkit for Zen 5 Ryzen processors includes the overclocking knobs from Zen Plus, PPT, TDC, and EDC, Zen 2, Boost Override and Scalar, Zen 3, Curve Optimizer, and the newly announced Curve Shaper for Zen 5. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we're just enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and, to a lesser extent, the TDC and EDC limit will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for Extended Profiles for Overclocking, and it simply enables higher performance for AMD with DDR5 platforms. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting. Note that, unlike in some other SkatterBencher guides, I could simply set EXPO 1 and run the memory kit at the EXPO rated DDR5 8000. Upon entering the BIOS, the boost frequency at one active thread is about 5463 MHz, and the average boost frequency gradually trails off to 5144 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 can boost to over 5.5 GHz, and all cores in CCD1 boost over 5.4 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. Despite the Ryzen 9 9900X having a TDP of 120 watt, the performance is still restricted by its power limit, especially in heavy all-core workloads. By enabling PBO, we can pretty much double the power budget. Combine that with enabling higher memory speeds, and it translates into pretty decent performance gains across the board. The geo-mean performance improvement is plus 3.98%, and we get a maximum benchmark improvement of plus 28.60% in Y-Cruncher. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 4933 MHz, and CCD1 effective clock is 4977 MHz with 1.158 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 229.2 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5083 MHz, and CCD1 effective clock is 5152 MHz with 1.237 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 237.7 watts. In our second overclocking strategy, we tune the Precision Boost frequency curve using some of the tools available in AMD's Precision Boost Overdrive 2. Fused maximum frequency, or Fmax, is one of those frequency limiters affecting the Precision Boost algorithm. Every chip inside your CPU has an Fmax, which includes the two CCDs as well as the IOD. The IOD typically governs the overall CPU Fmax. For the Ryzen 9 9900X, the IOD Fmax is 5650 MHz, whereas CCD0 is limited to 5625 MHz and CCD1 is limited to 5350 MHz. Boost Clock Override, or Fmax Override, is one of the tools available in the PBO 2 Overclockers toolkit. It allows us to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz. That's been available in steps of 25 MHz since forever, but it seems that with Ryzen 9000 we can now set it in steps of 1 MHz. The BIOS option still jumps in steps of 25 MHz, but with specialized tools, we can set it to any frequency in the operating system. With a plus 200 Fmax Boost Override, the new maximum boost frequency is 5850 MHz. Note that the Fmax Boost Override applies to all chips on package. So the new CCD0 Fmax is 5825 MHz, and the new CCD1 Fmax is 5550 MHz. It's important to note that the Fmax Boost Override simply lifts the frequency ceiling, and it doesn't act as an offset. At the end of the day, the Precision Boost algorithm still determines the eventual operating frequency. Scalar is a tool that allows us to override the warranted silicon stress level, or FIT. We can typically increase it to 10x the factory fused value. While the tool offers precise granularity, typically you'll find the available options to range between 1x and 10x in steps of 1 multiple. The effect of increasing scalar is that the Precision Boost algorithm more aggressively pursues higher voltages as it is less concerned with CPU lifespan. For Zen 5 granite-rich processors, it seems that scalar is making a comeback in the overclocking strategies because the primary limiter of the operating frequency is the operating voltage. When all cores are active, the maximum voltage is 1.355 volt. The maximum voltage when a single thread is active is 1.38 volt. The programmed fit value of this particular Ryzen 9 9900X is 6017.8. So with a 10x scalar, the new fit value is 60,178. We find that in an all-core workload, the maximum voltage increased to 1.365 volt. That's not a big increase, but in voltage-constrained scenarios, every little bit helps. Curve Optimizer has been one of the most important tools of the Precision Boost Overdrive toolkit. It's most commonly known for its undervolting capabilities, but on AMD Ryzen CPUs, it kinda also acts as an overclocking technology. To explain what I mean by that, let's start with the basics, the voltage frequency curve. Here's the default voltage frequency curve of my Ryzen 9 9900X processor. You'll find that there's in fact two distinct curves, one for each CCD. We can immediately make a simple and redundant observation. The higher the frequency, the higher the voltage. For example, CCD0 requires only 1.129 volt for 5 GHz. However, we need 1.355 volt for 5.5 GHz. Although it's not obvious from the VF curve, the maximum allowed voltage is 1.355 volt when all 6 cores in a CCD are active. The Precision Boost 2 algorithm utilizes the VF curve to find what's the maximum possible frequency at 1.355 volt. As I showed just a minute ago, we can use the Fmax Boost Override tool to increase the Fmax by another 200 MHz and extend the maximum allowed voltage using scalar. That further extends the default VF curves in theory from 5625 to 5825 MHz for CCD0 and 5350 to 5550 MHz for CCD1. However, the rules for Precision Boost still apply, so we do still have that maximum voltage limit. If we set a negative curve optimizer, we can shift the entire voltage frequency curve along the voltage axis, and suddenly we need a lot less voltage for every operating frequency. For example, at default, for 5 GHz, CCD0 needed about 1.129 volt. However, with a -30 curve optimizer for CCD0, we now only need 1.035 volt. The same applies to the other CCD. Moreover, the frequency is also boosting higher. The highest frequency with all cores in the CCD active has increased to 5750 MHz in CCD0 and 5550 MHz in CCD1. These higher frequencies are now possible because our curve optimizer undervolting pulled them below the voltage threshold. Curve Optimizer is a very powerful tuning tool. It's simple, but not simplistic. And the more you dig into how it works, the more intricate it becomes to deploying it in your daily overclock. Typically, we use Curve Optimizer by setting a negative value for your AMD Ryzen CPU. That helps in two ways. First, undervolting lowers the operating voltage, temperature, and power consumption. Second, as a consequence, the Precision Boost 2 algorithm can leverage the additional headroom to boost to higher frequencies. So you tend to get lower temperatures and higher performance. It's a win-win. But there are a couple of caveats when it comes to tuning with Curve Optimizer. First, Curve Optimizer impacts the entire voltage frequency curve, so it affects stability across a wide range of operating frequencies from 600 to 6000 MHz. The same curve optimizer value impacts differently across the curve. If you're lucky, your CPU's undervolt margin matches how Curve Optimizer applies the offset across the curve, and then you'll have a really easy time squeezing more performance out of your chip. But if the curve doesn't really match how the offset works, then it can become a little bit trickier to find the right Curve Optimizer value. Curve Optimizer is available on a per CPU, per CCD, and per core basis. For multi-CCD CPUs, I typically use the per CCD curve optimizer approach because the CCD undervolting capabilities can vary wildly. The manual tuning process for curve optimizer can become quite convoluted because it spans a wide range of workloads, going from light single-threaded workloads all the way to heavy all-core workloads. I want to emphasize this point and refer to my Ryzen 9 9950X overclocking guide, where I demonstrated that the VF curve changes depending on the workload. With dynamic voltage frequency scaling technologies like Precision Boost 2, it's vital to test a wide variety of scenarios as opposed to just a heavy all-core workload pushing the power consumption to its limit. Sometimes your all-core AVX workload can be entirely stable, but you get blue screens in games. I identified 4 typical workloads that tend to show early signs of instability. In this particular case, I found that Y-Cruncher BKT was the earliest indicator of instability. When testing, I increased the negative curve optimizer setting in steps of 5 points, then check stability with each of these applications. Once I find an instability, I back off on the curve optimizer and check stability across the benchmark suite. Upon entering the BIOS, the boost frequency at one active thread is about 5661 MHz, and the average boost frequency gradually trails off to 5316 MHz when all cores are active. In light single-threaded workloads, 5 out of the 6 cores in CCD0 can boost to over 5.8 GHz, and all cores in CCD1 boost to over 5.5 GHz. We reran the benchmarks and checked the performance increase compared to the default operation. Undervolting with Curve Optimizer is a Ryzen overclocker's best friend and has been for a very long time. It provides this Ryzen 9 9900X with a nice frequency and performance bump. The geomean performance improves by 5.5 percentage points, and we get a maximum benchmark improvement of plus 29.09% in Y-Cruncher. When running the OCCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5173 MHz and CCD1 effective clock is 5094 MHz with 1.103 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 227.8 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5376 MHz and CCD1 effective clock is 5238 MHz with 1.188 volts. The average CPU temperature is 95 degrees Celsius. The average CPU package power is 229.2 watts. In the third overclocking strategy, we delve into optimizing the memory subsystem. Now, the memory subsystem on AMD Ryzen CPUs consists of 3 parts: the Infinity Fabric, the memory controllers, and the system memory. They're most commonly referred to as the F-clock, the U-clock, and the M-clock or Mem clock. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 9 9900X, we can tune them independently. The fabric frequency or F-clock is generated by the SoC PLL, derived from a 100 MHz reference clock input. The reference clock is then multiplied by the F-clock ratio, which you can configure in the BIOS. The standard operating frequency of the Infinity Fabric is 1800 MHz, but on many motherboards you'll find it runs at or over 2 GHz when Precision Boost Overdrive is enabled. That said, it doesn't seem there's much overclocking headroom beyond 2 GHz. I managed to set 2.2 GHz for this overclocking strategy, however anything higher couldn't boot reliably, not even with voltage adjustments. Speaking of the voltage, the Infinity Fabric voltage is provided by the VDDG voltage supply, derived via an integrated voltage regulator from the VDDCR miscellaneous voltage rail. There's a total of 4 VDDG voltage rails available for manual adjustment. AMD Granite Ridge processors have 2 memory controllers, each providing 2 32-bit memory channels. The memory controllers are located on the I/O die. The Unified Memory Controller Frequency, or UClock, is derived from the UMC clock, one of the SoC PLLs. The UMC clock is driven by a 100 MHz reference clock derived from either an internal or external clock generator. The memory controller frequency is tied directly to the system memory frequency. It can run at either half or the same frequency. At default, the memory controller runs at the same frequency as the system memory at 2400 MHz. However, we find that when enabling EXPO, the motherboard auto rules will drop the memory controller frequency to half the memory frequency. We could easily force the memory controller to run at the same frequency as the system memory by setting uclock div1 mode to uclock equals memclock. However, that's only possible if we run the memory at around DDR5 6000. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on SoC for the various IP blocks, including the memory controller. The VDD-IO MEM voltage rail is related as it provides the external power for the VDD-P DDR5 bus signaling. A nice benefit of running DDR5 8000 with the memory controller at half the memory frequency is that we can run the SoC voltage lower as well. The BIOS auto rules will usually increase the SoC voltage to 1.3 volt to increase the overclocking headroom, but with DDR5 8000, we don't need that much voltage. In my case, I could lower it to 1 volt and still have a stable system. The last piece of the memory subsystem tuning puzzle is, of course, having a look at the memory timings. And for that, I rely in part on ASUS's memory presets technology. ASUS Memory Presets is an ASUS overclocking technology that provides a number of memory tuning profiles for a variety of memory ICs. Typically, it will adjust the voltage and the memory timings. The ROG Crosshair X870E Hero motherboard supports 14 memory profiles for a variety of memory ICs and configurations. Since we're interested in simply adjusting the memory timings, we can try the Hynix 7600 MHz 1.45 volt 2x16GB single rank preset. The Hynix 7600 memory preset turned out not to be super stable, as it would throw errors in OLCCT memory stress test almost instantly.
An error has been detected. An error has been detected.
But no cause for alarm, because we've seen this in previous overclocking guides as well. To fine-tune the timings, I try setting certain timings back to its EXPO value until I find the timings that caused the errors. Unfortunately, unlike with previous overclocking guides, I had to adjust quite a lot more timings to make the memory pass our target of 1 hour of OLCCT stress testing. Here's my final optimized memory timings for this particular system. After the memory tuning, our AIDA64 performance improved quite significantly. We got about plus 40% extra bandwidth and 20% lower latency by enabling EXPO, and then the memory tuning added another 20% improvement on top of that. Upon entering the BIOS, We reran the benchmarks and checked the performance increase compared to the default operation. As we've seen with other modern platforms, tuning the memory timings can have a not insignificant impact on system performance, especially in workloads which are memory dependent. We see this behavior in specific multi-threaded workloads like Y-Cruncher, AI Benchmark, and Geekbench. Also, we can see a decent impact in certain games like Homeworld 3 and Tomb Raider. The geo-mean performance improves another almost 3 percentage points, and we get a maximum benchmark performance improvement of plus 49.42% in Y-Cruncher. In our final overclocking strategy, I'm pursuing a manual overclock using OC mode. Now, there is an argument to be made that manual overclocking is kind of useless on AMD Ryzen CPUs. And that's because when we enable or switch to OC mode to set our manual configuration, we disable all automatic boosting technologies like Precision Boost, which means that we don't have the benefit of those high single-threaded frequencies. Instead, the maximum operating frequency will be our set clocks. Now, there are a couple of advantages to using OC mode. First, it's much simpler and usually faster than tuning with the advanced overclocking tools from Precision Boost Overdrive 2, like Curve Optimizer. Second, automatic overclocking and frequency boosting technologies can leave a little bit of margin on the table. We can exploit this margin and fine-tune it for application stability when manually overclocking with our specific hardware configuration. Lastly, sometimes the static voltage and frequency configurations run cooler than using a dynamic adaptive clocking technology. To better understand the performance tuning opportunities embedded in our Ryzen CPU, let's have a look at its clocking and voltage topology. The standard Granite Ridge platform has a 48 MHz crystal input to the integrated CG-PLL clock generator. The CG-PLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. This used to provide us with a 25 MHz clock granularity, but with Granite Ridge processors, we can now set the frequency in steps of 5 MHz or 0.05x. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. When we switch to OC mode, we disable all automatic precision boost frequency boosting technologies and rely solely on the manual frequency and voltage configuration. The Ryzen 9000 voltage topology relies on a combination of internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDDCR voltage rail provides external power for 3 internal voltage regulators. VDDCR CPU provides the voltage for the CPU cores inside the CCX. The voltage rail can work in either regular or bypass mode, but on Granite Ridge, it's always in bypass mode. That means the voltage is always equal to the VDDCR external voltage. On this motherboard, we can configure this voltage regulator in the BIOS. A crucial parameter is the VRM load line setting. The VRM load line is important to understand for 2 reasons: VDroop and undershoot. VDroop is the decrease in voltage when the CPU goes from idle to load. You want your CPU to be stable in all scenarios, so knowing the lowest voltage the CPU runs at is very important. After all, if the voltage is too low, the overclock won't be stable. Undershoot and its counterpart overshoot is a brief voltage spike that occurs when the CPU switches from idle to load or from load to idle. These spikes cannot be measured easily and usually require an expensive oscilloscope to detect. I highly recommend the Elmore Labs article titled VRM Load Line Visualized to see a great picture of undershoot and overshoot in action. While undershoot and overshoot are temporary spikes, an undershoot that's too low can cause instability. The VRM load line setting is relevant to this overclocking strategy because we're switching from Precision Boost to OC mode. That means the CPU is no longer regulating the load line itself, and instead we have to correctly configure it by ourselves. Choosing the proper manual voltage for our manual overclock is always going to be a trade-off between increasing the overclocking headroom, dealing with the thermal challenges that come with elevated voltages, and consideration of the CPU lifespan. It's with that last thought that we kick off our manual tuning process. Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we are tuning for. So the first step in our tuning process would be deciding on the stress test representing our worst case scenario. In this case, I picked the 30-minute all-CCT AVX512 CPU stability test because I found that even if I passed the AVX2 workload, AVX512 benchmarks like Y-Cruncher would still fail. The next step is to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. For the baseline settings, I look at the all-CCT stress test results from OLC strategy number 2. Here we find that the AVX2 workload ran at about 5.1 GHz with 1.1 volt. So I started the manual tuning process with a CCX ratio of 50x for each CCD, a VID of 1.2 volt, and a load line set to level 6. We find that gives a temperature of about 85 degrees Celsius and an effective voltage of 1.106 volt in all CCT AVX512. Once we know the maximum voltage, we can tune the CCX ratio. Simply increase the CPU ratio until the application shows signs of instability, then back off. This approach will give you the maximum stable per CCX frequency for a given voltage. In our case, we end up with CCD0 at 53.35x, CCD1 at 52.15x, and a core VID of 1.2 volt, which under high load drops to about 1.12 volt with load line calibration set to level 6. If we try to compare the VF configuration of this OLC strategy with the VF curves from OLC strategy number 2, we can see that we've configured a single VF point on the VF spectrum as opposed to define a curve that spans a range of voltage frequency points. Upon entering the BIOS, the boost frequency at one active thread is 5335 MHz, and the average boost frequency gradually trails off to 5275 MHz when all cores are active. In light single-threaded workloads, all cores in CCD0 run at 5335 MHz, and all cores in CCD1 run at 5215 MHz. We ran the benchmarks and checked the performance increase compared to the default operation. We see a pretty decent performance uplift compared to stock performance in most benchmarks. However, as expected, we also see some performance regression since the maximum frequency is now 5335 MHz, which is 290 MHz lower than the maximum 1T boost frequency with Precision Boost enabled. We got a maximum improvement of plus 39.44% in PY prime. When running the all-CCT CPU AVX2 stability test, the average CPU CCD0 effective clock is 5335 MHz and CCD1 effective clock is 5215 MHz with 1.2 volts. The average CPU temperature is 85.9 degrees Celsius. The average CPU package power is 210.6 watts. When running the OCCT CPU SSE stability test, the average CPU CCD0 effective clock is 5335 MHz and CCD1 effective clock is 5215 MHz with 1.2 volts. The average CPU temperature is 79.1 degrees Celsius. The average CPU package power is 198.5 watts. Alright, let's wrap this up. The AMD Ryzen 9 9900X has been in the market for quite some time. It was available at the launch of the Ryzen 9000 CPUs. Personally, I wasn't too interested in this particular SKU, and that's why I haven't made an overclocking guide until now, because it basically consists of two weaker CCDs. Either way, the CPU could enable EXPO 8000 out of the box, so that was very good. And one of the two CCDs actually had quite a bit of undervolting margin as well, so that was a lot of fun. And as we've seen with other Ryzen 9000 SKUs, looking more closely at the memory subsystem can actually have quite a big impact on certain all-core multi-threaded workloads like Y-Cruncher. Anyway, that's it for this video. I want to thank you for watching and the patrons and the YouTube members for their support. As per usual, if you have any questions or comments, feel free to drop them in the comment section below. I'll also put up a written version of this video up on my blog if you want to read through all my settings and benchmark results. And that's it. See you next time.